Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help everyone answer a question. What is electric potential? So this is meant to be just a conceptual video about what electric potential is. So for right now, what I'd like to do is ignore this stuff. This is stuff I'll be referring to later in the video. And we're going to start here with this coffee cup, believe it or not. Now, imagine that this coffee cup starts here at a height h off the ground. That coffee cup has a certain potential energy, and when you talk about potential energy, the first thing you typically do is define a datum. And it's pretty common for gravity type problems to define a datum maybe at the surface of the Earth. So we would say that this cup has a potential energy equal to mgh. And anybody that's had first semester physics has probably seen this quite a few times. Now, the gravitational force on this cup is down equal to mg. And if I, imagine the cup being dropped and accelerating down until it hit the ground, the work done by gravity would be the force mg times the distance h. And that work would be positive because anytime the force is in the direction of motion, in this case the cup's moving down, and the gravitational force is down, then the work done is positive. Now you'll notice that these are the same expression. So conceptually speaking, what potential energy is it's the work done by some conservative force as this object or particle moves to the datum. So keep that in mind, that effectively what that potential energy is it's a work term. Now I know that the technical mathematical definition for it is not quite that, but this is just meant to be a conceptual video, and conceptually that's what potential energy term is. It's a work term, and it's the work, in this case, that gravity will do on this cup as it moves from here to the datum. Now we're going to get rid of this and talk about now charged particles. So imagine, I've got some sort of point charge here that I'm going to say has a magnitude that I called capital Q here. Now, for the sake of this discussion, we're going to imagine it's got a nail in it or something. This can't go anywhere. So tack, tack, tack. This thing's not free to move. It's going to stay here for the remainder of this discussion. Okay. Now imagine I take another charge and I place it close to it, like here, where the distance between them now is that distance, is what I'm going to call r here. There's going to be a repulsive force between them, and the force direction on this particle will be this way because they're both positive and they're going to repel one another, and that's what we call the Coulomb Force. Now that same force exists down the left on this particle, but it's not important for the discussion here. This one's going to be staying put. Now, the Coulomb force, when you calculate it, it's directly proportional to both charges, falls off with distance squared. This is called Coulomb's law. So if I put this particle here at what I'm going to call position 1, and we release it, it will accelerate away. So, here's my kind of picture of that as this thing goes zipping off. Now, if you plot the Coulomb force, because it has this 1 over r squared, it has this type of shape to it. 1 over r squared, this goes to 0 when r gets big, or in math we say when it goes to infinity. So this curve looks something like this. Now, work, remember, is force times distance. When the force varies as the object's moving, it takes a bit more math. It's not, you can't just take like a force times a distance. It becomes an area under the curve problem, which is quite common calculus type of problem. So it's not important that we actually get a value. All we need for this discussion is to realize one exists. The work done by this force, the Coulomb force, as this particle moves off to just leaves, would be represented by this green area here. So this green area would equal the work done by the Coulomb force, and it's some positive number. And what that is this green area would represent the work done on this object as it moves away, or in fact, as r goes to infinity. And it's very common to define the potential energy at r equals infinity to be 0. And the reason why, well, you'll notice that the Coulomb force goes to 0 at r goes to infinity. So it's a natural place to put the data. So this green area represents the work done by the Coulomb force as this particle starts from this position and moves off to infinity. So that work done, just like the cup example, is equal to the potential energy of this system when this particle is at position 1. What we call the electric potential, which is represented by this capital letter V, is that potential energy per unit charge. And this is a property of the space around this charge. All right, so if I were to make myself like a circle around this charge, I could put this one anywhere on the circle, and if you let it go accelerating away, you'll get exactly the same force curve, exactly the same green area, exact amount of work done. Therefore, the potential energy of the system is the same for this charge anywhere on this circle. Now, that potential energy would be larger if this charge were larger, right? And for that reason, because we're looking for a property of only the space around this charge is divided out. So you take the potential energy, divide this charge out, and you get a number with units of joules per Coulomb. And that's what electric potential is. It's potential energy per unit charge. And the potential, in this case, would be the same anywhere on this surface. Now, it kind of looks like a circle, but it's really a three-dimensional surface. So maybe I'll try to add some dimension to it. You could actually put this particle anywhere on this three-dimensional surface, and it will have the same potential energy, and by the time you divide the charge out, you'll get the same potential. In fact, this surface around this charge is what's called an equipotential. So I'm going to try to keep this video short. It was just meant to be a short introductory video on what is electric potential. And my short answer is it's potential energy per unit charge. The potential energy equaling the work done by the Coulomb force as this particle accelerates away to infinity. So that's what electric potential is. Hope that this video helps you better to conceptually understand it. Have a great day.